Dear students, in this class we are going to prove that the characteristic of a ring R is n if and only if the order of the multiplicative identity in R is n. So let us begin. So first of all, we will assume that characteristic of the ring R is n, and we will prove that the order of the multiplicative identity of R is n. Now here the notation that we are going to use for multiplicative identity is 1, a usual one that we always use, somewhat like this. Now we have to prove that order of 1 is n in R plus. But in order to prove this, we are supposed to note one important thing, and this part will be required for the if part of the theorem as well as the converse part. So for any natural number m and any element of the ring A, how can you write ma? Ma can be written as A plus A plus A m times. But note that A is an element of the ring and the unity is actually 1. So therefore, how can you write A? And A can be written as 1 dot A, I mean 1 multiplied by A. Similarly, this A as well can be written as 1 multiplied by A, and this will be continued. So this is going to be again how many times? M times. Now we know one of the properties of ring that multiplication is distributing over addition. So by using that property, this A can be pulled out of all the brackets. So here we will have 1 plus so on 1. Remember, this 1 is unity of the ring, and this summation is going to be again m times. But 1 plus 1 so on plus 1 m times can be written as m dot 1. So what we have, ma can be written as m dot 1 into A. Remember, 1 is the unity of the ring. So in order to prove order of 1 is equal to n in R plus, what we have to do is we have to prove that n is actually the least positive integer such that n multiplied by 1 is equal to 0. Remember, we have to prove n is the least positive integer such that n multiplied by 1 is equal to 0. But by simple observation, we can see that we are having nx is equal to 0 for all x belongs to R, as characteristic of the ring is n. So in particular, if I put x is equal to 1, because 1 is actually an element of a ring, right? So in particular, if I put x is equal to 1 in 1, so what will happen? So in particular, put x is equal to 1 in 1 to get n multiplied by 1 is equal to 0. Now it remains to show that this n is actually the least satisfying this condition, and we are going to prove it by contradiction. So we will say, on contrary, assume that there exists an integer m greater than 0 less than n such that m into 1 is actually equal to 0, right? So we have assumed that there is some smaller positive integer than n satisfying this condition, and we are calling that integer as m. Now this should lead to some contradiction. Now what is the contradiction here? Note that from 2, what we are having actually? So m dot 1 is actually equal to 0, right? So what will be ma then? So ma will be equal to 0. So what we'll say, using 2, we have ma is actually equal to 0 for all a belongs to R, and remember, here m is an integer greater than 0 and less than n. So indirectly we got a contradiction. Contradiction to what? Since we are assuming characteristic of the ring R is n, it implies that n is the least positive integer such that nx is equal to 0 for all x belongs to R. But what we got here? We have one more positive integer which is smaller than n, satisfying the condition ma is equal to 0 for all a belongs to R. So what we'll say here, which contradicts to the fact that characteristic of R is equal to n. Thus, our assumption is wrong. So what should be right? Therefore, n is the least positive integer such that n into 1 is equal to 0, and therefore order of 1 is actually equal to n in the ring R plus, and that is exactly what we wanted to prove. Now we will go for the converse. Now we are going to prove the converse. So we will assume that the order of the multiplicative identity of R is n. Remember, for multiplicative identity we are using the notation 1. So I will say this is converse. So part 2, suppose order of 1, that is multiplicative identity of R, is n. What does it imply? According to definition, this implies n is the least positive integer such that n into 1 is actually equal to 0. Now what we have to prove here? We have to prove that characteristic of R is actually equal to n. Now what is the meaning of it? n is the least positive integer such that na is equal to 0 for all a belongs to R. Now remember, this is the equation 2 that we already have. From this equation we already have ma is equal to m multiplied by 1 outside the bracket a. Now the same result I will use for this integer n. So what I will have? So using 2 we can say that na is actually equal to 0 n into 1 into a for all a belongs to R, right? But what we have assumed? We have already assumed that n multiplied by 1 is equal to 0. So simply use this value. So after using this value, this will be equal to 0 multiplied by a, and which is equal to 0. So what we have proved? Therefore na is equal to 0 for all a belongs to R. But there is a catch, right? Remember, this n should be the least satisfying this condition. So again, in order to prove that this n is the least, we are going to take the help of proof by contradiction. So we'll assume that this n is not least, meaning there is some smaller positive integer than n satisfying this condition. So I will say, on contrary, assume that there exists an integer m greater than 0 and less than n such that this ma is equal to 0 for all a belongs to R. So in particular, let us put the value of a is equal to 1, which is our unit element. So what it will imply? It implies that m dot 1 is actually equal to 0, where m is an integer which is less than, and definitely m is positive integer less than n. Is it true? But remember, what we have assumed that the order of 1 is n, meaning n is the least satisfying this condition, but we got an integer smaller than n satisfying the condition, which is a contradiction. So which contradicts to the fact that order of 1 is n in R plus. Therefore, our assumption is wrong. So what should be right? Therefore, n is the least positive integer such that n is equal to 0 for all a belongs to R, and which implies characteristic of R is actually equal to n, and that is exactly what we wanted to prove.